thank you all for coming this afternoon. I know it's the last talk and we're all a bit tired after 2 days of presentations, so I'll try to keep it as short as I can. So the role of abduction in chaining multiple experiments. First, I'll say a few words about the main question, which is what strategy guides researchers when they're planning studies with multiple experiments? And studies with multiple experiments, I will abbreviate SME, so you don't have to wonder what this is in the slides. Then I'll say a few words why this problem is interesting. So why should we care about the strategy that guides researchers? Then I'll show you how we can model such a general strategy by applying a particular pattern of abduction. Then I'll try to show it again by an example. And this example is from the field of numerical cognition, and it concerns the discovery of the so-called snark effect. I'll tell you all about it in a minute. And then, of course, some conclusions. So, the main question. What strategy guides researchers when they, plan studies with multiple experiments? It seems that there is a lot of research in philosophy of science in the logic that guides researchers in doing a single experiment. But the question of how they plan multiple experiments or what strategy guides them in multiple experiments is not so well researched. So if we want in the philosophy of science to make a better description of what actually goes on in the sciences, we could, try to come up with such a model, or perhaps many models. As I've said here, perhaps there are different models which could account for the same thing, for the general idea of planning studies with multiple experiments. And these models could go on, but I will use an abductive pattern. And my work in this model is based on the works of course, Charles Peirce, Hintikka, and Gerhard Schurz. So, why should we care about this problem? So, why is it interesting? As I've said, it seems in most of the sciences, scientists use different experiments in the study of the same topic, and they serve different functions. So they use them to replicate previous results. They use them to test alternative hypotheses. They use them to specify empirical findings from previous experiments, and many other functions. So if we strive to make a general account of scientific experimentation, we somehow cannot forego the idea, what is the logic, what is the strategy behind such studies with multiple experiments. And here is a general model, which I have taken from Gerhard Schurz, which is called an and/or tree. And the idea is this. So the labeled nodes in the model correspond to literals. These are predicates with a constant. Here it is again. Here is a labeled node. Here is a name. Here is a predicate. Here is a labeled node, a name, and a predicate, and so on. The unlabeled nodes are conjunctions or disjunctions of the labeled ones. So here is a labeled node, which is a conjunction, in this case, the disjunction, in fact, between those. This one, unlabeled node, is a conjunction between those two nodes. And, arrows correspond to causal implicational laws, which means that the causal structure in the model is fixed. So we should say that this guy over here causes this one, and this causes this one. And the known facts in this model are represented by a plus sign. So in this model, we can find actually two known facts. This is this guy here, where we start, and this guy here on the bottom level. And those with an asterisk are, in fact, the abduced conjectures, or hypothetical abduced conjectures. Arc-connected arrows in the model, so like this one or this one, represent conjunction, and those arrows that are not connected with an arc represent disjunction. So this is an or connection, and this is an and connection. Numbers represent probabilities, obviously, and they do not add up to 1, which means that there is some probability, so there is some unknown residual probability in here. So as you see, this guy is known, so on this fact we know, and there are different facts that can lead up to it, but all of their probabilities do not sum to 1, because there may be some other hypotheses that we haven't really discovered or tested or thought about. So this is a very simplistic model. The idea in it is, in fact, the goal in the model is to find the best first search. So this is the shortest and the most probable route, which leads to the abductive conjecture T2A. So let's see again. We know this fact, and we need the shortest and the most probable route to this guy here. Obviously, this is the best first search throughout the model. So, however, at every intermediate step in the model, there could be many of those. So this tree that I've shown has just 3 levels, but there can be, in fact, many others. We may subject our conjecture to empirical testing. So what do I mean? We start from a known fact. We conjecture this one. We could empirically test it and then go ahead to the next level, choosing our probabilities and our route accordingly. Experiments, either groups of experiments or single experiments, may be considered as the steps in these 3, as the steps of the abductive process. These empirical tests or experimental tests may give a clue about how to redistribute probabilities for the next step. So we make an empirical test, we make a different probability distribution for the next level, or perhaps the probability distribution stays the same because we find no unexpected evidence, and we make the next step to the next level of the tree. The process is thus tractable in search spaces with exponential complexity, meaning even if you have on some level indefinite and in fact every next level gets exponentially more and more nodes, by empirically checking on every step that you make how the world actually is, so gathering evidence, gathering data, you could put constraints on the next level and so deal with exponential complexity. So every hypothetical conjecture, that is a node in the model, may be considered an answer to a research question. And I'll show you in a minute how this could be done. So every hypothetical node in the model could be an answer to a research question. And the research questions, in turn, are formed how? Well, this is Hintika's ideas. He says, well, it is tricky to do scientific research because you have to ask the right questions. And the right questions, a hint towards how to ask the right questions is, well, you have to consider which are the most probable answers that you can get from your data and form your questions accordingly. So this could be done, in fact, in terms of posterior probability. So you choose the most probable answer in term depending on how probable you expect its answer to be. So you choose the right question depending on how probable you expect its answer to be in light of the evidence you expect to obtain when empirically testing it. So, in fact, the one with the highest posterior probability wins. And here is an even simpler model, not as involved as Gerhard-Schurz. And let's say that we start from this guy here. This is a known fact. In fact, we know that this holds, and we want to consider our next research question. One of the things we could do is ask whether this guy that we know, this fact that we know, is due to this hypothesis here, which means that, in fact, that it is due to a conjunction of very improbable factors. So there are 6 of them here. Or we could try out and investigate whether it is that the fact that we know is the result of either of 2 considerably more probable factors. which is, I'm sorry, this has some kind of delay. Okay, so either we consider this one or consider this one. This is, in fact, the conjunction of very improbable factors, and this is, in fact, the conjunction of two considerably more probable ones. The goal is, again, to find the best first search, and it is obviously true here. So this is how we optimize our probabilities. We go here, we empirically test, and if this distribution stays the same, we go to here and empirically test that one, and maybe go to different levels altogether. So this is how the idea goes. So this is how the model should work. And next I wanted to, well, show you, because this is all very abstract and theoretical, I wanted to show you how a particular example from science could probably fit the model that we're looking at. So I'll talk about the discovery of the snark effect, but first a few words. This discovery is taken from the field of numerical cognition. Numerical cognition is a field in cognitive science which investigates mental representation of numbers, numerosities, magnitudes, mathematical disabilities like dyscalculia, and so on. And in the early 90s, in the field of numerical cognition, it was found out what they called the spatial numerical association of response codes, in short, the snark effect, by Stanislav Dehaene and others and collaborators. Stanislav Dehaene is a big figure in in numerical cognition and in cognitive science. Put simply, the effect is this. The researchers asked people to do a parity judgment task, so they presented to them centrally numbers from 1 to 9, and they asked them to differentiate between odd and even numbers. And they found out that the subject's responses were modulated by the task-irrelevant magnitude of the presented numbers, meaning the subjects were told to look for parity, odd or even only, but it seems that they were influenced by the magnitude of the number. It was on the smaller side, it was 1 or 2. They were, in fact, faster with their left hand and slower with their right. And if it was a magnitude, a bigger magnitude like 8 or 9, they were in fact faster with their right hand and slower with their left. And this was called the snark effect. The main dependent measure, yes, of course, they measured reaction time. And how they found out this effect was, well, their original study had 9 experiments, which they said were systematically designed, I quote. And the systematical design was, they grouped them in 3 groups, experiment 1 and 2, 3 to 7, and 8 and 9. And these groups had to answer different research questions, in fact. So they said, in experiment 1 and 2, we want to check how parity information is extracted. So how the brain processes parity information. Is it calculated online? So is it calculated on the spot? Or is it retrieved from long-term memory? So these were the 2 hypotheses that they considered seriously as an answer to this research question. Experiments 3 to 7 were combined to show how parity and magnitude information relate to each other. And this is where they found the snark effect. So this is where they found that magnitude actually influences parity. And this discovery puts constraints on further theoretical models of number processing. So this result put constraints on what they could test on the next level. And the last 2 experiments actually checked whether reaction time varies with the input notation of the target number. So they presented subjects with Arabic numbers and with numbers written in words, and they tried to check how reaction times could vary. And this is how the design of the study could fit into a model of abductive pattern, as I have shown you. So what they knew when they began the study were 2 types of models of architecture of number processing. And the 2 hypotheses that they considered seriously, so the question they wanted to ask is, how is parity information extracted? Is it retrieved from long-term memory, or is it calculated online by using general mental calculations routines? So these are the hypotheses that they wanted tested. And Stanislav Dian, who was the leader of the project, had a higher support for the hypothesis that it is, in fact, retrieved from long-term memory, as it somewhat kind of, well, that was the case after the experiment, that they found out that more or less this is the case. So we could say that, of course, I would not add probabilities here because I wouldn't speak of the subjective probabilities of the researchers themselves, but judging by the literature, Stanislav Dian found this one rather the more probable one, so they tested whether this or this with a preference to retrieving from long-term memory. So they found out that more or less it seems that parity information is retrieved from long-term memory, and then they proceeded to the next level and to the next research question, which was, well, what is the relation between parity and magnitude? And of course, the two possibilities, logical possibilities, is either there is no relation or they are in some form interdependent, so we should expect an interaction between the two factors. And they found an interaction between parity and magnitude, and part of this interaction was in fact the snark effect. So the next level that they wanted to test is, well, okay, we found that parity and magnitude interact with each other, but is this somehow dependent on the input notation of the target numbers? So if we show them Arabic numbers and if we show them words, will this somehow have some kind of impact on the reaction times? So the three hypotheses that they considered here is, that could be considered here, is either, well, the input notation will have no effect, so it's all the same whether you show the subjects Arabic numbers or if you show them verbal notation. And the other two are shorter RT, so shorter reaction time, meaning the subjects were faster with the Arabic notation, and shorter reaction time, meaning the subjects were faster with verbal notation. And of course, common sense says that, well, this is actually quite improbable. If you have to see a word rather than an Arabic numeral, you ought to be a bit slower because you have to read the word in order to react. So being faster with verbal notation really doesn't make sense. This route here gets really a very low probability. It's either no effect, which doesn't even make sense, even before the experiments, because, well, you have to read the word in one case, and in the other case, you see the symbol and react. So there should be some effect, and they found, in fact, that there is some effect. Subjects were, in fact, faster with Arabic numerals than with verbal notation. And so the best first search through such a tree is, in fact, from the known, we know this models of processing, so we test this hypothesis here, then we test this one here, then we test the shorter RT with the Arabic notation. And of course, this is a very simplistic model of what they did, actually. If you read through the study, you'll see that every experiment that they did, in fact, answered not only the main question of the group of experiments, but also other questions. So the model is simplistic. It kind of fits what they did, but in order to actually describe the depth of the study, it should be pretty much more involved, and there should be even more levels in it. But all the same, I think I can, well, show that it seems to work in this case. And, well, I promised to keep it short, so let's go for the conclusion. A philosophy of science strives to provide a general account of scientific experimentation. I believe we should investigate the strategy of scientists when they chain multiple experiments. This particular pattern of abduction, this model that I showed you, seems to be able to capture this general strategy. And this model is capable to account for some actual scientific cases, such as the discovery of the snark effect that I showed you. And that's it. Thank you.